Hello guys, we're doing the now at home assignment number 17. This is new material. This is going over the exponential equations. So you may have seen this before. You'll see that it isn't really too much, honestly. There's just some definitions you need to know at the top of the page. For example, horizontal asymptote, horizontal asymptote, exponential growth, and exponential decay. So you may have heard asymptotes already before, but an asymptote is just a line that the graph approaches. So a horizontal asymptote is a horizontal line that the graph approaches. You have two different types of exponential equations, a exponential growth and an exponential decay. So growth is just an increase, decay is a decrease. So later on in the assignment, you'll see some word problems. That'll be one of the first things you need to do is decide if it's a growth or a decay. So here are just really our basic equations for our growth and decays. Notice here the right-hand side, it's going up for growth, and the right-hand side is kind of going down for decay. Now for this as well, we have two different types of equations. Y equals a times b to the x, and y equals a 1 plus r to the t. Here's the thing. These are technically the same equation. These are technically the same equation. Yes, one of them has a b and one of them has an r and a t, but these are the same. They're just used in different scenarios, which you'll see in a bit. Regardless, a is always your starting value, so that's true for both of them. So that is also your y-intercept. B is going to be your rate of change. And then over here, R is our rate of growth. For both of these, our rate of change or for our growth, we need it in a decimal. And if you forgot how to change a percentage to a decimal, remember, like if I give you, I don't know, 35%. To change that to a decimal, we are technically dividing by 100. You may have learned it as you take the decimal at the end, move it 2 places to the left. So that now becomes 0.35. So 35% is the same thing as 0.35. And then finally here, we also have our t variable, which represents time. This is important, and I highly recommend it every single time. Whenever you see your t variable for time, go ahead and write out what that time is. So is it your time in days, seconds, years, months, weeks, whatever? Some questions may want to trick you and say it's just a different type of time altogether. So that being said, the decay is the same thing. I mean, except that this one is just a subtraction sign. That's it, because you are decaying, you're decreasing. Now, with these first four, it's okay if you don't have a calculator, because decimals will help you out. So let's look at the first one right here. Y equals 3 to the x. Now, I'll show you how it looks like on decimals. So y equals 3 to the x. Let me get my keypad out real quick. All right, sweet. So notice with this equation here, I have a y-intercept of 0, 1. Again, y-intercept with 0, 1. And let's go ahead and find the x-intercept. It looks like, oh man, it looks like the line is touching the axis, doesn't it? Well, let's zoom in here real quick. So, okay, it's not touching there. Okay, it's not touching there. Notice here there's still like a little space in between the axis and the graph. Zoom in more, there's still that little space. Here's the thing. If you were to click on Desmos and like drag your cursor along, it's saying that you do have an x-intercept. But actually, if you zoom in, there is not an x-intercept. The reason why is because that x-axis, or the equation y equals 0, has an asymptote. So that's what I meant by the definition of asymptote. My graph right now is decreasing on the left side such that it's getting so close to my y equals 0, but it's never going to equal y equals 0. Look at that. It's never on the x-axis. It's never going to equal it. There's always that space there. There's always that space. And when it looks like it's getting close to the x-axis, we zoom in more and there's still space. So that's why we had that asymptote. It's just definition. So let's try to draw it. No, it will not be perfect, but just try your best. I care about that y-intercept, and I know that I'm never going to touch the x-axis. I'm going to go up in the right direction. So here, I do not have an x-intercept. My y-intercept is 0, 1. Again, the y-intercept was 0, 1. My domain, here's the thing. Remember, for this, it's always going to the left in an infinite direction. And on this right side, yes, it's going up, but it's actually also going towards the right. So my domain is all real numbers, and that's going to be the case for all your exponentials. So like we did with quadratics, you can go ahead and do the same thing, like on all these. Say your domain is always all real numbers. So with this here, my range, I'm actually going to say my horizontal asymptote first. So like I said earlier, my horizontal asymptote was the x-axis or the equation y equals 0. My equation is never going to touch that line y equals 0. It's going to get close, but it's never going to touch it. The reason why I did the asymptote first is because now I can figure out what is my range. The range is all the possible y values. So all the possible y values here is going to be all the numbers that are positive. Awesome. And it's not going to be any negatives. So it's going to be all the numbers greater than 0. And notice I'm not going to put an equal sign. I'm not going to say y is greater than or equal to 0, because my y value cannot be equal to 0 because there's a asymptote there. And then finally, is it a growth or a decay? Well, it is a growth. And that'll be it for number 1. Let's look at number 2. It's going to be 1/4 to the x. 1/4 to the x. So 1, 4, not 1, parentheses. We'll do this here. Perfect. Wow, that is not perfect actually. There it is. Perfect. So with this here, again, find your y-intercept. It's at the same point, 0, 1. Notice that the right side is now going down, but while the left side is going up. That means it's a decay. But look again on our right side. It looks like it's touching the x-axis. But when we zoom in, actually, there's that space between the graph and the axis here. So that means I do not have an x-intercept. I saw that my y-intercept was 0, 1. My domain is always all real numbers. So real quick, let me try to draw this. Again, will it be perfect? Nah, but it's going to be close enough. Sweet. My range, again, since I have a horizontal asymptote at y equals 0, that means all my values of y must be greater than 0. It will never be below 0, and it will never equal 0. And finally, since that right-hand side is going down, it's going to be a decay. Now let's look at number 3. Here's the thing. Just by looking at the equation for number 3, I already know that the y-intercept is going to be 0, 2. That's a bad 2. The reason why, this value out front, that is always your y-intercept. Notice up here, my y-intercept was not a 3. It was a 1. And it was not a 1/4. It was a 1. Technically, there is a 1 times 3 right there, and there's technically a 1 times 1/4. So here, the 2 was there, so I knew that that 2 was my y-intercept. If you don't believe me, well, let's just have someone smarter than me verify it, which in this case is, it's 1/3, right? Yeah. So 1/3 to the x. Perfect. If you look there, we see that our y-intercept is 0, 2. Now with this here, again, it's a decay, so the right-hand side is going down, and it looks like it's touching the x-axis, and it looks like it does equal 0, but it actually doesn't. There's a space right there. So that means with my graph, let's fill out what we know. There is not an x-intercept. We always have a domain of all real numbers. And let me draw this graph just so you can see. Perfect. So my range, again, it's going to be every value greater than 0, solely because we have a y-intercept. So we have an asymptote at y equals 0. That right-hand side is going down, so it's decay. One other thing I can tell us decay off the bat is this number right here, the 1/3. If that number is between 0 and 1, that means it's a decay. If you notice up here, the number was a 3. Since it was greater than 1, it was a growth. Notice here is a 1/4. That meant it would be a decay. And with that knowledge, I answered all of them right. Perfect. And with that knowledge on number 4, since this, okay, green, is a 2, that must mean it's a growth. And since we have a 3 out here, we saw that, I'll do this color, this 3 was representing the y-intercept. I could probably take a wild guess and say we don't have an x-intercept, but in case you're doubting me, it's 3. Yeah, cool. In case you're doubting me, let's double check. Perfect. We see here the x-intercept is 0, 3, and it looks like it has an x-intercept, but it actually doesn't. We're being lied to, unfortunately. But it's totally fine because we can just work with it. So 0, 3. My domain always for exponentials is all real numbers, unless we have a real world situation. And then my range, again, it's going to be y is greater than 0 solely because we have an asymptote at y equals 0. And that's 1 through 4. 5 through 8, we are just evaluating. We did this 2 weeks ago, but now in this case, we have exponentials. So f of x equals 3 to the 1/2 x. And I want to figure out what is f of 2. So let's do a different color here. F of 2. That means every place I see an x, replace it with a 2. So that's 3 times 1/2 squared. Please, please, please do the 1/2 squared first. Do not multiply 3 times 1/2. That will get you a wrong answer. 1/2 squared is going to be 1/2 times 1/2, which is 1/4. 3 times 1/4 would be just 3/4. Sweet. Next one here, 6g of 0. That means for a g of x equation, actually will stay consistent. G of x was 2, 5 to the x plus 1. So that means here, we want to find g of 0. Every place you see an x, we replace that with a 0. This is a nice little throwback to our exponential, our exponent properties. Anything to the 0 power equals 1. And since we need to do the step of exponents first, 5 to the 0 becomes just 1. 2 times 1 is 2, and then 2 plus 1 is 3. Finally, here in number 7, we have an h of x equation. H of x equals 3 to the x minus 2. That's fun. Our goal here is to figure out what is h of negative 4. So 3 to the negative 4 minus 2. Negative 4 minus 2 would be negative 6. And then 3 to the negative 6. Remember, if it's a negative exponent, to make it a positive, we flip it, and it would now become 1 over 3 to the 6. If you want to reduce that more, you can, just so we make it as nice as we can. So 3 to the 6, I think that's 729. Let me double check. It is, so that becomes 1 over 729. Awesome. Awesome. Number 8, f of 2 plus g of 1. I'm not going to work out f of 2 again because I just did it over here. So f of 2 is 3/4. I just did that. G of 1 here is, well, we haven't found g of 1, so let's find it again. G of 1 equals 2, 5 to the 1 plus 1. So 5 to the first power is just 5. 5 times 2 is just 10. And 10 plus 1 is 11. Now we need to add f of 2 plus g of 1. So take your result from f of 2, which is 3/4. Take your result from g of 1, which is 11, and add the two together. We're adding a number to a fraction. Now, you really don't use mixed numbers anymore, so let's keep this as an improper fraction. My first step when adding two fractions, I recommend putting it over 1 if you don't have it already. Now, I want to get a common denominator. Between 1 and 4, I would like 4 to be my common denominator. So I'm just going to rewrite this. To change this 11 over 1 to have a denominator of 4, I'm going to multiply both the bottom and the top by 4. That first stays the same, but this second fraction now becomes 44 over 4. Now that we have common denominators, this is nice because I can just keep the bottom the same and add the top. So 3 plus 44 is just 47. And keep it as a fraction. We want to stay as accurate as possible. Finally, let's finish up with some word problems. So our first step in this is we need to identify if it's a growth or a decay. From there, we'll just identify each of the individual pieces, like the starting value, the rate, and then the time. So let's read this one out. A savings account has $8,500 and gains 2.5 interest each year. So even just knowing your knowledge of bank accounts, do you want bank accounts to grow or decay? We generally want bank accounts to grow. And it says it here, a savings account gains. So that means it's a growth. So if you forgot, our growth equation is these two things. I'm going to go ahead and use the bottom one. So that equation was, let's write it here, y equals a 1 plus r to the t power. What that means is I have a starting value, which is a, I have a rate, which is r, and have a time, which is t. So let's identify each of those things. So let's do that in orange. My starting value, I'm going to start off with 8,500. And I want to, we'll do that in green, increase by a rate, which is 2.5%. And what's my time? My time is going to be in years. So that's my T. So replace what you know in your equation. My A value was 8,500. And like I said earlier, we want our rate as a decimal. So let's change that 2.5% to a decimal. Remember, to change a percentage to decimal, we're dividing by 100, or you could just move the decimal 2 places to the left. So to change that 2.5% to a decimal, I could take that decimal, move it 2 places to the left. So that is now 0.025. So that means here on my rate, I'm adding 2.5% or 0.025. Now, I want an equation that's going to have a variable that's changing. So as time increases, that means my time is changing. And let's simplify a little bit because we can just condense this. We have 8,500. 1 plus 0.025, that is just 1.025 to the t, where t is your time in years. This is what I meant. I recommend going ahead and saying that last part. Say that your time is in years. We wrote a function that models this part. Y equals 8,500, 1.025 to the t. Now let's actually get some practical stuff. So let's say you're trying to invest and you invest 8,500 with the interest of 2.5 each year. How much money will be after 4 years, 6 years, or 12 years? So this is a good thing. Let's say you're a freshman, you need to invest this. How much will you have when you graduate? So after 4 years, we had that equation. We'll do that in a different color. Y equals 8,500, 1.025 to the t. And we're investing, and we're trying to see how much we have after 4 years. This is where you have to use a calculator, type it into decimals, whatever calculator you have. Again, I'm just using a calculator. So that means after 4 years, I'm going to have 9,382 point. So my calculator says 0.40957. Normally, I want you to keep 3 decimal places. However, we're talking about money, so let's just keep 2. So after 4 years, $9,300. That's pretty good. Let's try the next. Let's try what happens after 6 years. We'll do this here, just because I don't want to write it. And try that one more time. Perfect. So with this here, I want to figure out what happens where instead of having 4 years, we waited 6 years. So same thing, just plug it into your calculator, but instead of saying 4, we say 6, and we'll get 9,857.39. It's not bad. In those 2 years, we gained about a good, what, $500? Just about. It's not too bad. And then finally here, what happens, my bad, 6 years. What happens after 12 years? A mistake I see people do all the time is they want to just multiply the total they got from 6 years. They want to multiply that by 2 to get your total for 12 years. That is incorrect. Do not multiply 9,857.39 by 2. take your rich equation and plug in 12. We'll end up getting 11,431.56. It's a pretty good investment. You'll learn more about compound interest in Algebra 2. Number 10, population of mice on a farm was approximately 250. You got a cat. Population decreased to 3% per day. So, is it a decay? Let's go yellow. Is it a decay or a growth? Well, the population decreased. So we got smaller. We were decaying our population. So the two formulas are very similar, except that we now have a subtraction sign in the middle. Now let's find each part. So the A is our starting value. Let's find the starting value. We started with 250. So that's our A. And then next we had a rate of what? 3%. So that's our rate. And then for a time, it was days. Our time was in days. So let's write out and plug in everything we know. My A value was 250. 1 minus my rate. My rate was 3%. Let's change that 3% into a decimal. Again, take that decimal point and move it 2 places to the left. So that's 0.03. So that means here we'll do 1 minus 0.03 to the t. And yes, you can condense this a little bit more, because 1 minus 0.03 is 0.97. And go ahead on this question. It's important to note that our t is the time in days. So if they give us a certain amount of time in days, we just plug it in. If they don't give us the time in days, we need to change it to be the time in days. The reason why this is important, because let's look at part B. How many mice will be on the farm after 4 weeks? So do not do this. Do not plug in 4 in for your t, because that t is representing time in days, but they give us time in weeks. So what I'm going to do here is, I didn't give you enough space. I'm terrible, I know. So just move this B. We'll do the work down here. There's so much space here. So how much mice will be in the farm after 4 weeks? Well, let's change those 4 weeks into days. I'm about to do a thing called dimensional analysis. You'll learn more about that in the chemistry. It's just unit conversion. Let's convert from weeks to days. I know that in 1 week, we have 7 days. Therefore, in 4 weeks, we'll have 28 days. I just multiplied 4 times 7. That's nice, because now in my equation, I just say it was, how much was it, 250? Yeah, 250. We could just say to the 28 power. So I have a decimal on this. This is kind of up to you. You generally don't have a decimal percentage of a mice. So what I will do is I'll have a little, I can't do that. It's a curvy sign. That means approximation or approximately. It's 106.548. I'm going to say approximately 106. Again, I'm not going to put the decimal because we're talking about mice, which is a whole number amount of something. So let's just keep it at 106. And then finally here, it says use the table option in your calculator to figure out how long it will take for the cat to clear all the mice, but we don't have a calculator. So how can we answer this question? Use Desmos. So 250, we type it in here. We have 250, 0. I believe it was 97, correct? Yes. And I'm going to go ahead and just say to the x. So notice here, you have to zoom out a little bit. There's our equation. So the x, again, is what's going to tell us x is the time and the y is the amount of mice. So as the time increases, our mice decrease. Like at day 126, we have about 5 mice left. So let's try to see where the number for y is below 1. You will not get it perfectly, but try to get as best as you can. Where is it at? And 180, probably 182, I'm guessing. Yeah, 182. At 182, it's, if I can keep steady, it's 0.978, which is below 1. So C, using Desmos or a calculator, did I spell that right? Approximately 182 days. You don't have to change that to weeks, just leave that days. Last two, population of 300 rabbits doubles every year. Let's see, is it a growth or decay? If it's doubling, it's increasing. That means it must be a growth. So write out your base equation for growth. Usually this color. Y equals A. So in this case, actually, I'm going to switch it up on y'all. I'm going to use B. Remember, here, we had two different equations. Y equals A to the B to the X, and Y equals 1 plus R to the T. And I said that these two were the same thing. B is just your rate of change. So here, my rate of change, well, actually, let's just find each individual part. We have 300 rabbits, so that's starting. What's our rate? Our rate this year is we're doubling. We're doubling. And we're doing every year. So here, my starting value again will be 300. And if I'm doubling something, that means multiplying with the 2. And to the, you can say t or you can say x, doesn't really matter in this case. Just to be consistent with the equation up top, I'll go ahead and say x, just so I'm consistent. Regardless, x is the time in years, so it doesn't really matter. It's just a variable. We wrote a function, so that was for part A. My bad, I should have put it next to it. How many rabbits will be there after 4 years? So in our equation, y equals 300 2 to the x. I'm going to say 300 and then 2 to the 4th power. Again, plug this in your calculator. Do not do 300 times 2 and do that to the 4th. Instead, we'll get 4,800 rabbits. That's a lot of rabbits. Jeez. How about 6 months? Again, do not plug in 6 for x because it's the time in years. But now it's saying, hey, what about 6 months? So let's change this months into years. So again, this is dimensional analysis. 6 months. We know that there's 12 months in 1 year. So that means, and for 6 months, that is equal to 1.5 years or 0.5, whatever you want to do. So in our equation, we will plug in 1/2 or plug in 0.5, whatever one's easier for you to plug into your calculator. You'll still get the same answer either way. We'll get approximately 424. Again, there's a decimal attached to that, but I'm not doing the decimal solely because we got rabbits, we got whole things, actual things. But approximately after 6 months, 424 rabbits, which is still a lot. Finally, let's finish up with number 12. We got a bike that costs $300. Each day the bike is bought, it receives a 20% discount. So think to yourself, is my cost increasing or decreasing? The word discount, thankfully the word discount, it means a decrease. So that means we have a decay here. So I'll go ahead and go back to the formula we love and like so much. Y equals A, 1 minus R to the T. Let's fill out each of our parts here. So we have an A value. That's our starting. We start at $300. I guess that's a good price for a bike. What's our rate? We receive a 20% discount. And what's the T, the time? You have to look carefully on this one, but the time is every day. So with this here, let's plug in what we know. Our A value is $300. Our R, which is the rate, is 20%. And reminder, 20% is going to be 0.20 as a decimal. And that's to the T. So here, Y equals 300. 1 minus 0.2 is 0.8. T, and the T is the time in days. Let's look at part B. It says, after 12 days, what will the cost of the bike be? So, again, I didn't give you much space. My bad. My bad here. 300. So then we want to plug in 12 for our T. And this is an absurd amount price because I would totally love this. If I plug in 12 for T, I get $20 and 62 cents. Now, obviously, we know that will probably never be the case, which brings us to part C, which I'll do here, part B, and then we'll do part C. Will the bike ever be $0? I will not answer this question. I want you to answer it. Think like a business owner. Do you want your bike that you're selling to be at $0? So oh gosh, you tell me and explain your reasoning. If you give me a proper explanation, I'll give you credit. Yes or no, you tell me. This was assignment number 17 over exponential equations. We'll finish up next week with one more over exponential, and that will be it.